The last topic of this chapter is the power. By definition, the power is, okay, we use symbol as a capital P. The power at a specific time is the rate of the work done. All the work done per unit time. So we can just write down as the power equal to the dW by dt, right? So where W here is be the work done. So the work done we have unit as the joules and the time is second. The unit of the power is the joules per second. We call it as the watt, okay? Or we use the symbol as the capital U. So you need to be careful about this. If we have W as a variable, it will represent the work done, okay? But if we have W as the unit, it will represent the watt, which is the unit of the power, okay? So that's how the power is useful, right? How the power is useful. Let's consider this. If I have an object, okay, and then if we have a force, let's say the force F, that try to push this object right into this direction, okay. So let's consider the two cases. When, okay, the first case, if the object just move slow. So now you can see that the work done by this, right, equal to the force F and then times the displacement, okay. But now if the object just moves slowly, right, it means that the time is large, so the power will be small, as you can guess. On the other hand, if the object is moved very fast, right, so just move from here to here is really fast, then again, right, the work of the second case is be the same as the first case, because the work is equal to the force and then time this displacement, right? It just be equal to the first case. But now the time taken is different right now. The time in this second case is less than the time in the first case, okay? So it means that the power in this second case should be greater than the power in the first case, okay? So what is the physical meaning of the power? Okay, so now you can guess that the power is a quantity that tells the capability, right, of an engine, okay, or of the force or whatever, okay. So it means that if you have the high power, so in a unit of time, right, the work is going to be really large. But then if you have the low power, so in a unit of the time, right, the work done will be small, okay. So let's do the conclusion. Okay, the larger the power, okay, then the more the work done per unit time. Okay, so this will be the physical meaning of the power. Okay, so now let's come back to this question. Okay, so we said that the power, right, equal to the power equal to the dW, right, by dt. Okay, so in this case, if the object, right, is displaced by the displacement equal to the dr. So let me use which one? This one. Okay, so if the object is displaced okay, so now if the object is displaced okay, so if the object is displaced by the displacement equal to the dr, right, equal to the dr, then we can just write down the dW, right, to be equal to the force F and then dot product with the dr, okay. So now we can just move the dt to the dr here, right, so we have the dr by dt. So then what is the dr by dt? It's just equal to velocity v, right? It's just equal to velocity v here. So then we can get another equation of the power, which is the power equal to the force F and then the product with the velocity V, and that's it, right? So this is another form of this equation above here. Okay, so consider these examples. Okay, an elevator with the mass equal to the 1,600 kilogram, right, carries the passenger, the total mass, the 200 kilogram. Why there's a constant, the 4,000 Newton force resisting the motion of the elevator on the way up. Okay, so let's draw the picture here. We have an elevator, okay, and we have a passengers inside this elevator. Yep, something like this. Okay, so we said that the total mass, right, just equal to the 1,600 and then plus the 200 kilogram. Okay, so total mass is 1,600, oops, and then plus the 200, which is equal to the 1,800 kilogram. This is the total mass, and we have the resistive force, right, which is equal to the 4,000 Newton here. So we have the resistive force. Let's say that it's just into this direction. Okay. Okay. Equal to the 4,000 Newton. Okay. So find the electric power delivered to the motor in order to raise the elevator and passenger with a constant speed, the 3 meters per second. Assume that the efficiency of the electric motor equal to the 75%. Okay, so let's say that we have the cable here. So we have the cable, right? Let's try to pull the elevator up. Okay, and now this cable is connected to the motor. Actually, I should just draw something like this. Let's say that we have the motor here. We have this motor and this one. Okay, so this is the motor. Okay, and then this cable is connected to the motor, just wrapping around the motor, something like this. Then again, right, we must have the tension due to this cable, which is equal to the T, for example, and then we should have the weight, right, due to the mass of elevator and the mass of the passenger. The weight just equal to the 1,800, right? This is the mass, and then times the gravity G times the 9.81. Okay, so now we just want to find the electric power, the power of this motor delivered to we just want to find the electric power delivered to the motor here. Okay, and we said that the efficiency of the power of the electric motor equal to the 75%, right? So what should we do? Okay, so what should we do? So one thing that you can see that the power of the motor depending on this force, the force of the cable. Okay, so then if we can find the power of if we can find the tension here, then we can find the power of this motor. Okay, if we can find the tension, then we can find the power of this motor. But then how, right? Then how? Let's find the tension. Find the tensions in the cable. Okay, because the elevator is moving up with the constant velocity, it means that the net force must be equal to the 0, right? Then from this picture we can get that the tension must be equal to the 4000 Newton and then plus the 1/800 times the G, right, which is equal to the 4000 and then plus the 1800 times the 9.81, which is equal to, okay, the 2.16 times 10 to the 4 Newton. So this is the tension in the cable. Okay, this is the tension in the cables. So then what else, right? Now we just want to find the power. Okay, we just want to find the power of the motor. Okay, so let's find the power of the motor. Okay, let's find the power of the motor. So then again, we know the force, right? And then we know the velocity equal to 3 meters per second. Then we can use this equation to find the power of the motor. Okay, so let's say that the power of the motor equal to, okay, from this equation, right, it's just equal to the force, the 2.16 times 10 to the 4, and then times the velocity of this elevator, just 3 meters per second. So we just multiply with the 3.00 meters per second, right, which is equal to what? Equal to the 6.49 times 10 to the 4 watt. Okay, this is the power of the motor. Okay, but then we need to find the electric power delivered to the motor. So how? Okay, so find the electric power delivered to the motor. Okay, so we said that the efficiency of the motor is equal to the 75.0%, right? It means that if the electric current, right, gives the electric energy equal to the 100 joules, the electric motor will get the energy only the 75 joules, and the other 25 will be lost via the heat or the sound or whatever. Okay, so now with this, right, we know the efficiency of the electric motor. We can say that the efficiency, right, which is equal to what, 35.0%, right, the 0.750, it must be equal to, okay, the electric power that's delivered to the motor, right? So this one is with the denominator, and then for the numerator, okay, it's gonna be the power that the motor gets. Okay, so this is called the efficiency of the power of the motor. So then finally we can get that the electric power is equal to, okay, the 6.49 times 10 to the 4 watts, right, and then over the efficiency equal to the 0.750. So then the answer is equal to 8.66 times 10 to the 4 watts. Okay, so this is the answer. So you can see the number from the answer, right, that the electric power must be greater than the power of the motor. Okay, because there's some energy loss, right, during the transfer from the electric power to the power of the motor here, right, by heat or by the sound or by the light or whatever. Okay, so that's why this value must be less than this value. And that's all for this chapter.